Hey guys, welcome. 10-2 video. Let's get started. We're increasing our knowledge on finding areas of shapes. We learned about parallelograms and triangles, and now we're moving in to some more different shapes, which we kind of use the same basis to help us out. So here we go. Lower that down a little bit. That was a little bit better. So here we go. First one, make sure you write these down. We can find the area of a trapezoid when you know its height and the length of its bases. So again, height has to be denoted with the perpendicular segment, and a trapezoid is kind of like a triangle, and we just kind of cut the top off. And because we cut that top off, we have basically what looks like two bases. And we're going to kind of go in and get into this in further detail in a moment, but our formula is 1/2 the height times base 1 base 2. So we get that half thing. That's kind of because it's kind of like a triangle. But we're also going to do some kind of neat stuff here too. If you see, we see a little right triangle up here in this picture, which might pop up in our example problem. So make sure you get that one written down. Let's go ahead and take a look at our last two. And we have rhombus and kite combined together. We're going to focus more primarily on the rhombus because we haven't really talked about kite. But the area of a rhombus here is diagonal 1 times diagonal 2, and then we take half of it. Again, we're also going to notice here we see embedded in this rhombus there's not only one right triangle but 4 right triangles. So trig might come back in a way of maybe Pythagorean theorem, SOHCAHTOA, or special right triangles. So we'll go ahead and take a look at those as we get into our first problem. So let's take a look at finding the area of a trapezoid. These can be very straightforward or it can be kind of confusing. So here we go. What is the approximate area of Nevada? So it actually is kind of like a trapezoid. We see we have two non-parallel sides. So these would be my two non-parallel sides. And then we have two parallel sides, and that's kind of what makes up a trapezoid. So we are going to use our formula of 1/2 the height times B1 plus B2. Now it doesn't matter which one's base 1 or base 2, so let's call this base 1, and we can call this base 2, and the height is the distance between them using perpendicular, so this is our height. So all we got to do is plug it in and solve. So we get 309, add these two together. Doesn't matter the order because addition, again, order does not matter because of that commutative property of addition we learned way a long time ago. And once we get it to here, we can go ahead and calculate. Now we have to do this in the right order. Parentheses will go first, 205 plus 511. So we get 716. And boom, 1/2. Multiplication order doesn't matter either. And if I took half of 309, well, that's going to be an odd number. So I'm going to go ahead and multiply 719 by 309, and then I'm going to divide that by 2. So we get an approximate area. So I'm going to use approximate signs of 110,622 miles. And we got to put that squared on it. So this is 110,622 square miles. Is approximate distance, or sorry, approximate area for Nevada. All right, let's take a look at another problem. Okay, so here's our second problem, and this is the area of a trapezoid, PQRS. We have a problem. I don't have a height. Now I know if RQ was there, I would have a height, we could solve for it, but we don't. What can we do? Well, they gave me this angle measure here, and I'm glad they did. If I break this down into a 90-degree right here, I actually have a special right triangle. So if I draw this out a little bit larger, we have 60 degrees, 90, 30 degrees, and this would be my height. That is a horrible looking 30, so let's redraw that. My apologies. That's much better. So my question is, what's this distance from here to here? Well, if you think about it, 5 is all of this. So if you take 5 away from 7, we're going to get 2. So the length here is 2. So we can actually solve this using special right triangles because this is a 30, 60, 90. So across from 60, we call that x rad 3. Across from the 30 is x, and across from the 90 is 2x. Now I want to know the height of the triangle, so I'm going to actually erase a lot of this and put this line back in there, right? That was what we're doing right here. And if x is 2, we're going to know the height is going to be 2 rad 3. And now we have enough information to go ahead and put this in the equation. So let's go ahead and write this out. Area equals 1/2 the height, B1 plus B2. Okay, so now we got 1/2. The height here is now 2 rad 3. And base 1 is going to be 5 plus base 2, which is 7. Again, must do parentheses first, so add those two together, we get 12. And 2 rad 3, and take half of it, that's going to end up with just rad 3 if we combine those two guys. And rad 3 times 12, that will just, we'll call that 12 rad 3. Remember, whole numbers and radicals, they don't actually combine with each other. And we can leave this in the simplest radical form. We're going to call this square meters because we are dealing with area. So there we go. Kind of a nice refresher that we have special right triangles appearing yet again. So they didn't go away fully. But we had to evaluate to find that too. So that was kind of a tricky question. That would be a good one to go over just in case we see that one again very soon. Let's go ahead and look at this last one, finding the area of a rhombus. And pause that there. And so we have a highway occupancy vehicle, HOV lines, that's the carpool lane, is marked by a series of diamonds. So here's our diamond right there. Paint on the pavement. What's the area of the HOV lane diamond shown at the right? 1 second, let me see if I can get this. Okay, so here we got the picture by itself. So we got 2.5 here and 6.5. Now, if you guys remember, these are going to split up pretty nicely, but we have a right triangle embedded in here. And so we want to go ahead and find the diagonals because our formula, if we recall, is area equals 1/2 diagonal 1 times diagonal 2. And in this picture, we can find the second diagonal. So if we get our right triangle here, we get 2.5. We got 6.5. Could I find the other side here for my diagonal? And we could. And this is going to be x squared. Using Pythagorean's theorem, we can find the second leg, or the unknown leg, to help us out. Okay, so we're going to go ahead and grab our calculator. 2.5 squared is going to give us 6.25. And 6.5 squared is going to give us 42.5. Oops, 42.5. There we go. And that's plus x squared. Subtract it, and we're going to get, I'm going to bring it back up here, x squared equals 36, and so x will equal 6. So we get 6 as our length right here. Okay. Now in a rhombus, these segments are going to be congruent. So if this is 6, we know that this is 6 because diagonals bisect each other. So that's 6, and then this is 2.5 as well. Okay. So let's give ourselves a little bit of space. So I'm going to go ahead and erase this portion here. So hopefully you guys wrote that down. So let's erase that. Okay. So let's look at our diagonals. Our diagonal 1 is 6 plus 6, which equals 12. and diagonal 2 is going to be 2.5 plus 2.5, which is going to equal 5. So there's our two diagonals. We just got to use those to set up the equation. So we get 12 multiplied by 5, and then we're going to take half of that. Okay? And so 12 times 5 is 60, and then we take half of 60, and we're going to get 30, and this is in square feet. Okay. Alright guys, make sure you're ready for the warm-up tomorrow. We will have questions like this, so be prepared. Again, we reviewed Pythagorean's theorem today and special right triangles, so chapter 8 didn't fully disappear from us, so make sure you guys are ready. Alright, good job. We'll see you later. Mr. Smith, signing out.